You are listening to the continuous feedback loop, elevating software through constant improvement. Subscribe to keep up to date on our latest audiobooks. The continuous feedback loop, elevating software through constant improvement. In the bustling, ever-evolving world of software development, where new technologies emerge at breakneck speed and user expectations are constantly pushed to new heights, one concept stands as the silent, yet profoundly powerful, engine of progress. Feedback. We encounter feedback in our daily lives without a second thought. A chef tastes a dish to adjust seasoning. A musician listens to a recording to refine their performance. A driver adjusts their steering wheel based on the feel of the road. In each instance, information about an action, its outcome, or the environment is received, processed, and used to course-correct or improve future actions. This simple mechanism is fundamental to all learning and adaptation. But in software, feedback isn't just about making minor tweaks. It's about ensuring that the digital products and services we create are not only functional and robust, but also truly useful, relevant, and delightful to the people who use them. It's about building the right thing and building that thing right. Historically, software development often operated much like building a house with a blindfold on. Architects would draw plans, builders would construct based on those plans, and only once the house was fully erected would the future homeowners get to walk through it. Imagine discovering at that late stage that the kitchen was too small, or the bathroom was on the wrong side of the house. This Big Bang approach to delivery meant discovering problems, or even fundamental misalignments with user needs, far too late, when changes were astronomically expensive and time-consuming. The digital landscape, however, is far more dynamic than bricks and mortar. Users' needs change, markets shift, and competition is fierce. Waiting until a product is finished to get feedback is a recipe for irrelevance, frustration, and ultimately, failure. This is where the concept of continuous feedback loops comes in. What is a continuous feedback loop? At its heart, a continuous feedback loop, CFL, in software development is a systematic process of collecting, analyzing, and acting upon information about a product, process, or team at every stage, with the goal of rapid, iterative improvement. It's about creating a constant, flowing dialogue throughout the entire software development lifecycle, from the initial glimmer of an idea all the way through to a system running in production and beyond. Think of it like a sophisticated, self-adjusting thermostat. A traditional thermostat might simply detect if a room is too cold or too hot and turn the heating or cooling on or off. A continuous feedback loop thermostat, by contrast, observes the temperature constantly, compares it to the target, adjusts the output incrementally, and even learns from past adjustments to anticipate future needs more efficiently. It doesn't wait until the room is freezing or boiling before reacting. It maintains a comfortable equilibrium through continuous sensing and adjustment. Similarly, in software development, a CFL isn't just about fixing bugs at the end of a project. It's about sensing, actively gathering information from users, tests, systems, and team members, analyzing, understanding what that information means and identifying patterns or problems, acting, making informed decisions and implementing changes or improvements based on the analysis, observing, monitoring the impact of those changes, adjusting, refining the approach based on new observations, restarting the loop. This process never truly ends. Software is a living entity, constantly evolving, and so too must the mechanisms for its improvement. Why do continuous feedback loops matter? The shift towards continuous feedback isn't merely a trendy methodology. It's a fundamental paradigm change driven by the realities of modern software. Its benefits are profound and far-reaching: enhanced quality. Catching defects and misunderstandings early in the development process drastically reduces the cost and effort of fixing them. Imagine finding a small typo in a requirement document versus discovering a critical security flaw in a live system. Early feedback is a powerful preventative measure. Increased speed and agility. By integrating feedback constantly, teams can iterate faster. Instead of long, drawn-out cycles followed by massive overhauls, they make small, frequent adjustments. This allows them to respond swiftly to changing market conditions, user preferences, and emerging technologies. greater relevance, and user satisfaction. When users are part of the feedback loop from the very beginning, the end product is far more likely to meet their actual needs. This leads to higher user adoption, stronger engagement, and ultimately greater business success. It fosters a sense of co-creation. Reduced risk. Continuous feedback helps identify potential problems, technical, functional, or business-related, before they escalate into major crises. It's like having an early warning system that constantly scans for threats. Improved team morale and collaboration. When teams receive immediate feedback, they learn faster, feel more connected to the impact of their work, and can quickly see the results of their efforts. This fosters a culture of shared responsibility, continuous learning, and mutual respect, breaking down traditional silos between departments. Cost efficiency. While implementing CFLs requires an initial investment in tools and cultural change, the long-term cost benefits are significant. Fixing problems early is always cheaper than fixing them late. Avoiding the development of features nobody wants or needs saves immense resources. Consider the story of a well-known online retailer that, years ago, used to perform major website updates only a few times a year. Each update was a huge, nerve-wracking event, often involving weeks of testing and the anxious hope that nothing would break. When things did go wrong, fixing them was a monumental task, impacting millions of customers and costing untold sums. By contrast, that same retailer now deploys changes to its website hundreds, sometimes thousands, of times a day. How? Through sophisticated continuous feedback loops that allow them to test small changes rapidly, monitor their impact in real time, and roll back immediately if anything goes awry. This agility is a direct result of embracing continuous feedback. The journey ahead. Throughout this book, we will explore the various facets of continuous feedback loops, peeling back the layers to understand how they operate across the entire software development spectrum. We'll delve into the historical context that highlighted the desperate need for these loops, specific techniques and methodologies for gathering feedback during planning, design, coding, testing, and deployment, the critical role of production monitoring and user engagement in refining live systems. Crucially, we'll examine the cultural shifts and mindset changes essential for making these loops truly effective, going beyond just the tools and technologies. We'll also address common pitfalls and how to navigate them, as well as how to measure the tangible impact of embracing this continuous approach. By the end of our journey, you will have a clear understanding of why continuous feedback is not just a desirable practice, but an absolute necessity for anyone involved in building software today. You will be equipped with the knowledge to champion and implement these powerful mechanisms, transforming how your teams deliver software and, ultimately, elevating the quality and relevance of your products. Let's begin by understanding the path that led us here, the evolution of software development, and the challenges that birthed the imperative for continuous feedback. The journey of software development hasn't always been one of agile innovation and constant responsiveness. For many decades, the industry embraced an approach that, while logical in theory, often proved brittle and unresponsive in practice: the waterfall model. To understand why continuous feedback loops became not just desirable but essential, we must first appreciate the limitations of this traditional approach and the subsequent revolutions that redefined how we build software. From cascades to catastrophes, the limitations of waterfall. Imagine building a skyscraper. You wouldn't pour the foundation, then start on the 50th floor, then go back to digging a basement. Construction is inherently sequential and deliberate. It starts with comprehensive architectural plans, followed by foundation work, then structural erection, internal outfitting, and finally, inspection. Each phase must be completed and signed off before the next one begins, much like water cascading down a series of steps. Hence the name, waterfall. Early software development adopted a similar, highly structured, linear sequence. Requirements gathering. All software features and functionalities were defined and documented upfront. The belief was that once documented, they would remain stable. Design. Based on the requirements, detailed architectural and system designs were created. Implementation, coding, developers wrote the code according to the designs. Verification, testing. Once coding was complete, the entire system was put through a rigorous, often lengthy, testing phase. Maintenance. After deployment, any bugs found or new features requested were addressed. On paper, this seemed robust. It provided clear phases, measurable progress, and extensive documentation. However, in the dynamic world of software, the waterfall model proved to be riddled with critical weaknesses, primarily due to one fatal flaw: delayed feedback. Think of our skyscraper builder. If they realized during the final inspection that the building was supposed to be a hospital, not an office block, the cost of correction would be astronomical, if not impossible. Similarly, in waterfall, requirements changed. They always do. User needs evolve, market conditions shift, and new technologies emerge. Freezing requirements at the project's inception meant that by the time the software was delivered, it might no longer be relevant or solve the current problems. Late discovery of defects. Bugs or fundamental design flaws often weren't found until the very end, during the testing phase. The further along in the process a defect is discovered, the exponentially more expensive and time-consuming it is to fix. A coding error discovered during design is trivial. The same error discovered by a user in production can be catastrophic. Lack of user involvement. Users typically didn't see working software until near the very end of the cycle. This meant that assumptions about their needs might be entirely wrong, leading to products that functioned perfectly but were useless to their intended audience. Siloed teams. The handoff nature of waterfall fostered disconnection. Requirement analysts would throw specifications over the wall to designers, who would then throw designs over the wall to developers, and so on. This led to misunderstandings, blame games, and a lack of shared ownership. The result: projects that were late, over budget, and often delivered software that missed the mark. The Big Bang release, where years of work culminated in a single, massive deployment, became a source of immense anxiety and risk. The Gentle Revolution. The rise of Agile. The frustrations with waterfall's rigidity led to a grassroots movement among software practitioners. They recognized that software was not like building a physical structure. It was more akin to guiding a ship through ever-changing seas. This collective wisdom coalesced in 2001 with the publication of the Agile Manifesto, a declaration of 4 core values and 12 principles that prioritized human interaction and continuous adaptation over strict adherence to rigid plans. Agile methodologies, such as Scrum and Kanban, brought about a revolutionary shift: iterative and incremental development. Instead of one long cycle, work was broken down into short, time-boxed iterations, often 1 to 4 weeks, called sprints. Each sprint aimed to deliver a small, working increment of software. Customer collaboration. Users and stakeholders were no longer passive recipients but active participants, providing feedback on each increment. This ensured the software evolved in the right direction. Responding to change. Agile embraced change as inevitable. Instead of fighting it, teams were empowered to respond to new information and adjust course frequently. Cross-functional self-organizing teams. Developers, testers, and product owners worked together closely within the same team, fostering shared understanding and reducing communication overhead. Crucially, Agile fundamentally accelerated feedback. Sprint reviews allowed stakeholders to see and react to working software every few weeks. Daily stand-ups provided quick internal team feedback. Retrospectives offered regular opportunities for the team to reflect on their process and continuously improve. The focus shifted from avoiding change to responding to change faster, and this speed was directly enabled by more frequent, shorter feedback loops. Breaking down walls. The emergence of DevOps. While Agile transformed the development side of the equation, a critical bottleneck remained. Development teams were building software faster than ever, but getting it into production, the realm of operations teams, was still often a slow, manual, and error-prone process. The traditional divide between dev, who wanted to build and release new features quickly, and ops, who prioritized stability and uptime, often created a wall of confusion, leading to friction and delayed deployments. This challenge gave rise to DevOps. More than just a set of tools, DevOps is a cultural movement emphasizing collaboration, communication, and integration between development and operations engineers. Its core tenets include automation of the software delivery pipeline. Automating tasks like building, testing, and deploying code reduced manual errors and increased speed. This led to practices like continuous integration, CI, and continuous delivery, CD. Monitoring and observability, treating the deployed software in production as a source of invaluable feedback. Tools for logging, metrics, and tracing became paramount to understand system health and user behavior. Shared responsibility. Development teams became more involved in the operational aspects of their software, and operations teams provided more input into the development process. Blameless postmortems. When incidents occurred, the focus shifted from assigning blame to understanding the systemic causes and learning from failures, ensuring the loop was completed through process improvement. DevOps took the iterative feedback philosophy of Agile and extended it across the entire lifecycle, from code commit all the way to a running application in the hands of users, and then looped that operational feedback directly back into the development process. It completed the circle, making the flow of information truly continuous. Continuous feedback loops, the unsung hero. It becomes clear, then, that continuous feedback loops are not simply a byproduct of Agile or DevOps. They are the backbone that enables these modern approaches to thrive. Without rapid and pervasive feedback, Agile would merely be a series of short, isolated development cycles without a mechanism to truly adapt to evolving needs. DevOps would be just a collection of automation tools, without the crucial intelligence derived from production systems being fed back to improve the product and processes. The high cost of delayed feedback, once the Achilles heel of waterfall, is precisely what CFLs are designed to eliminate. By integrating feedback at every single stage, from the first conversation about a new feature to the monitoring of a live system, we dramatically reduce the risk of building the wrong thing, building it poorly, or discovering costly errors too late. Problems become small, manageable adjustments discovered early, rather than catastrophic failures uncovered at the end of a long, arduous journey. This evolution from rigid, sequential development to highly adaptive, iterative, and collaborative approaches underscores a fundamental truth about software. It is never truly finished. It is a living artifact that must constantly adapt and improve, and the engine for that constant improvement is the disciplined pursuit of continuous feedback. Having understood the historical imperative, we can now delve into the practicalities. Our journey begins at the very first steps of software creation, the planning and design phases, where the earliest and most impactful feedback can be gathered. Chapter 3, the blueprint phase, feedback in planning and design. In the vast ecosystem of software development, there's a powerful but often undervalued truth. The earlier you discover a problem, the cheaper and easier it is to fix. This simple principle is encapsulated in the concept of shifting left, moving feedback and quality assurance processes as far left as possible on the development timeline, ideally to the very beginning. The planning and design phases are the initial canvases where ideas take shape, and thus, they represent the absolute best opportunity to gather crucial feedback that can prevent costly missteps down the line. Imagine building a house again. It's far simpler, faster, and cheaper to erase a line on a blueprint than it is to demolish a newly constructed wall because it was placed in the wrong spot. Similarly, a misplaced comma in a requirements document is insignificant compared to a fundamental design flaw that requires rewriting thousands of lines of code. The blueprint phase is where we establish the foundation and the very purpose of our software, and getting early feedback here ensures we are building the right thing for the right people. The power of shifting left. Shifting left feedback means proactively seeking input from stakeholders, potential users, and even technical experts before significant time and resources are invested in development. This isn't just about catching errors. It's about validating assumptions, understanding nuances, and ensuring alignment with strategic goals and user needs. So, how do we gather this vital early feedback? 1. Understanding your audience. User stories, personas, and empathy maps. Before a single line of code is conceived, it's crucial to deeply understand who we are building for and why. User stories. These are simple, concise descriptions of features or functionalities from the perspective of an end user. Typically formatted as a type of user, I want some goal, so that some reason. User stories force us to articulate value from the user's perspective. The active conversation around creating and refining these stories with product owners and stakeholders is a powerful feedback mechanism, highlighting forgotten requirements or conflicting desires. Example: as a casual reader, I want to easily share articles on social media so that my friends can see interesting content. Personas: these are fictional, generalized representations of your ideal or typical users, based on real data and interviews. A persona might include demographic details, behaviors, motivations, and pain points. Developing personas involves asking key questions and gathering input from sales, support, and marketing teams, providing shared understanding and empathy within the development team. Empathy maps: these tools push beyond simple demographics, diving into what users see, hear, think, feel, say, and do. By collectively filling out an empathy map, teams gain a deeper understanding of user contexts, anxieties, and desires, uncovering unstated needs that might otherwise be missed. The discussions and debates that arise from creating these artifacts constitute invaluable feedback loops, ensuring everyone is building towards a common, user-centric vision. 2. Visualizing ideas. Prototyping, wireframing, and mockups. Humans are visual creatures. Describing a complex interface with words alone is prone to misinterpretation. Visual aids provide tangible points for discussion and feedback. Wireframes: these are skeletal, black and white layouts that focus on the structure and hierarchy of a user interface, indicating where elements like buttons, text, and images will go. They are intentionally low fidelity to keep the focus on functionality and flow, not aesthetics. Showing wireframes to stakeholders can quickly reveal if the proposed navigation or layout is intuitive. Mockups: stepping up in fidelity, mockups introduce colors, fonts, and images, giving a more realistic sense of the final visual design. While not interactive, they help gather feedback on the look and feel, ensuring brand consistency and user appeal before development begins. Prototypes: these are interactive, though often non-functional, simulations of the finished product. Prototypes, ranging from clickable wireframes to sophisticated dynamic models, allow users and stakeholders to experience the software's flow and functionality. This is arguably one of the most powerful, shift-left feedback tools, as it allows real users to test workflows and discover usability issues long before any code is written. Observing a user struggle with a prototype is far more insightful and actionable than receiving a bug report weeks after launch. 3. Shaping the architecture. Design critiques and architecture reviews. Feedback isn't just for external users. It's also crucial internally, especially for the intricate technical foundations of the software. Design critiques: these involve presenting design concepts, UI/UX, system flows, to peers and relevant stakeholders for constructive evaluation. The goal is to identify potential usability issues, inconsistencies, or missed opportunities early. Crucially, a positive critique environment fosters open discussion without personal attachment to designs. Architecture reviews: technical architects and senior developers present proposed system architectures, data models, and technology choices to a group of peers and experienced professionals. This process uncovers potential scaling issues, security vulnerabilities, performance bottlenecks, or integration challenges before they become entrenched in the codebase. This peer-level technical feedback ensures the system is not only functional, but also robust, maintainable, and scalable. 4. Validating the core idea. Concept testing. Before committing significant resources, it's vital to know if the core idea itself resonates with the target market. Concept testing: this involves presenting a raw idea, concept, or value proposition to potential users to gauge their initial perception, interest, and understanding. This can be done through simple surveys, interviews, or even an explainer video showing the envisioned product. The aim is to validate the problem you're trying to solve and confirm that your proposed solution is desirable to your audience. This helps avoid building something nobody needs or wants, sidestepping a fundamental failure early on. Case in point, the retail app redesign. Consider a team tasked with redesigning a major online retailer's mobile app. In the past, they might have spent months designing and developing the new app in isolation, only to deliver it and find that users struggled with the new navigation, or that a highly touted new feature was completely overlooked because of poor discoverability. This traditional approach would result in massive, expensive reworks post-launch. Instead, this modern team embraced early feedback. They started with customer support data and user interviews to build detailed personas and empathy maps, pinpointing key pain points like difficult product search and a clunky checkout process. This early feedback highlighted what problems users truly had. They iteratively created wireframes and low-fidelity prototypes of potential new navigation flows and checkout experiences. They brought in a small group of actual users for prototype testing. Through observation, they quickly discovered that what seemed intuitive to the designers was confusing to users. For example, a new Express Checkout button was completely missed because of its placement. This user feedback was immediate and undeniable. They held internal design critiques where UI designers and developers collaboratively tore down and rebuilt interaction patterns for clarity and efficiency. Finally, senior architects conducted a technical review of the proposed data flow for the new checkout system, identifying a potential bottleneck that could have caused major performance issues under peak load. By iteratively gathering and acting on feedback at each of these left-shifted stages, the team refined their designs, avoided integrating flawed assumptions into the code, and launched an app that was not only aesthetically pleasing, but genuinely intuitive and efficient for its users. The cost of fixing a navigation error in a prototype was hours. In a live app, it would have been millions in lost sales, developer time, and reputational damage. The blueprint phase isn't just about drawing lines. It's about drawing the right lines, and continuous feedback ensures that we're using the collective intelligence of our users and experts to guide our hand. Once the blueprint is solid, we move to the next critical stage: crafting the code itself, where a different set of feedback loops comes into play. Chapter 4, Crafting Code, Feedback During Development. Once the blueprints for our software are refined and validated through early feedback, the tangible work begins, transforming designs and requirements into functional code. This phase, often seen as the core of software development, is where the detailed construction takes place. Just as a master artisan relies on constant inspection and adjustment while shaping raw materials, software developers need immediate, actionable feedback to craft high-quality, robust, and maintainable code. In the fast-paced world of modern software, waiting for a week-long testing cycle to discover basic coding errors is inefficient and demoralizing. The goal during the development phase is to provide the fastest possible feedback to the developer, often within seconds or minutes, allowing them to detect and correct issues right at the source, preventing them from escalating. This fosters a culture of fail fast, learn faster, where small mistakes are quickly identified and rectified, becoming learning opportunities rather than impediments. Let's explore the crucial feedback loops active during the code crafting process. The developer's first line of defense: unit testing. Imagine building a complex machine, like a car engine. You wouldn't assemble the entire engine and then, for the first time, try to start the car and see if it works. Instead, you test individual components, the spark plugs, the pistons, the fuel injectors, in isolation, ensuring each part functions correctly before integrating them. Unit testing applies this principle to software. A unit test is a small, automated piece of code written by the developer to verify that a specific, isolated unit of application code, e.g., a single function, method, or class, behaves exactly as expected. These tests are incredibly fast to run and provide immediate feedback to the developer. If a developer writes a new function and its corresponding unit tests, they can run those tests instantaneously. If a test fails, they know exactly which small piece of functionality is broken and can fix it immediately. This rapid feedback loop allows developers to iterate quickly, refactor code confidently, and build robust foundations, knowing that their core logic is sound. It's the most granular and fastest feedback available directly to the person writing the code. 2. The automated editor. static analysis, and linting. Even the most meticulous developer can introduce subtle issues or diverge from established coding standards. This is where automated code guardians step in. Static analysis tools examine code without actually executing it. They scrutinize the source code for potential bugs, security vulnerabilities, like SQL injection risks, performance anti-patterns, and adherence to best practices. Think of it as an automated code reviewer that can spot complicated structural problems or deviations from architectural principles. Linting tools, a subset of static analysis, focus specifically on code style, readability, and immediate syntax errors. They enforce consistency in variable naming, formatting, like indentation and brace placement, and highlight common pitfalls. Many modern development environments integrate linters directly, providing real-time visual feedback as the developer types, underlining potential issues in red or yellow, much like a spell checker in a word processor. These tools provide continuous, objective feedback directly within the developer's workflow, helping to maintain code quality, improve readability for future developers, and catch common mistakes before they even leave the developer's machine. 3. The wisdom of the crowd, code reviews. While automated tools are excellent at catching mechanical issues, they can't assess the elegance, maintainability, or conceptual correctness of code in the same way a human can. This is the realm of code reviews. Before a developer's code changes are fully integrated into the main project codebase, another developer, or multiple developers, reviews it. This involves examining the logic, style, design choices, efficiency, and overall approach. Code reviews are not about finding fault, they are about quality assurance, catching bugs, potential issues, and design flaws that might have been missed by the original developer or automated tools. Knowledge transfer. The reviewer gains an understanding of the new code, spreading knowledge across the team. The original developer often learns new techniques or better approaches from the reviewer's suggestions. Consistency and standards. Ensuring that the new code aligns with the team's coding standards, architectural patterns, and design principles. Shared ownership. Fostering a sense of collective responsibility for the quality and maintainability of the codebase. The feedback from a code review can range from minor stylistic suggestions to significant architectural changes. It's a critical human-driven feedback loop that elevates the collective quality of the codebase and strengthens team cohesion. 4. Real-time collaboration, pair programming, and mob programming. Sometimes, the fastest and most effective feedback comes from direct, real-time collaboration. Pair programming involves two developers working at a single workstation. One developer, the driver, writes code, while the other, the navigator, observes, reviews, and offers suggestions on the fly. They switch roles frequently. This immediate, continuous dialogue acts as a constant, tight feedback loop, preventing mistakes before they can even be typed, fostering shared understanding, and often leading to higher quality and more elegant solutions. It's like having a built-in, real-time code reviewer. Mob programming extends this concept to an entire team or a significant part of it, working on the same task, at the same computer, at the same time. While one person types, the rest of the mob acts as navigators, collectively deciding what to do next, designing, coding, and problem-solving together. This extreme form of collaboration ensures that every decision benefits from multiple perspectives, leading to incredibly tight feedback loops and accelerated knowledge spread across the team. 5. The heartbeat of modern development, continuous integration, CI. As individual developers write code and receive feedback, their changes eventually need to be combined into a cohesive whole. This is where continuous integration, CI, plays a pivotal role, serving as a crucial, automated feedback loop for the entire team. CI is a development practice where developers frequently integrate their code changes into a central repository, typically multiple times a day. Each integration is then automatically verified by kicking off an automated build process, which includes running all unit tests, integration tests, and static analysis checks. If the build or any test fails, the CI system immediately notifies the team or the developer responsible for the breaking change. This means early detection of integration issues. Instead of discovering conflicts and bugs when trying to merge weeks of work, Issues are found and fixed within minutes or hours of being introduced. Confidence in the code base. If the CI build is green, meaning all tests passed, the team knows the integrated code base is in a working and stable state. Rapid feedback on changes. Developers get immediate confirmation if their changes have inadvertently broken something elsewhere in the system. CI ensures that the collective code base is always in a known, releasable state, acting as a constant health monitor. It transforms the often painful integration hell of traditional development into a smooth, continuous flow. The culture of fail fast, learn faster. All these feedback mechanisms, from the personal unit test to the collective CI build and code review, contribute to a critical cultural shift. Embracing fail fast, learn faster. This isn't about making mistakes deliberately, but about designing processes that lower the cost of failure, making it cheap and quick to discover an error. Accelerate learning from failure, ensuring that once an error is found, the lessons are immediately incorporated. When feedback is rapid and constructive, making a mistake is no longer a setback, but simply another step in the learning process. It fosters experimentation and reduces the fear of breaking things, knowing that automated guards and supportive teammates are there to catch issues and help learn from them. This empowers developers to be more productive, innovative, and confident in their craft. With our code now being crafted and integrated with robust feedback loops, the next crucial step is to ensure it works as intended. This brings us to the comprehensive world of testing, where broader feedback loops validate functionality, performance, and security. Chapter 5: The Quality Compass. Feedback and testing. With the code crafted and continuously integrated, the next crucial stage is to rigorously test it. While unit tests and static analysis provide immediate feedback to individual developers, as discussed in Chapter 4, proper testing goes far beyond. It's about simulating real-world scenarios, validating functionality, assessing performance, identifying security vulnerabilities, and ultimately, ensuring the software not only works as intended, but also meets the needs and expectations of its users. Testing is a multifaceted feedback loop, acting as a quality compass that guides the development process. It provides objective data on the health, robustness, and correctness of the software, helping to catch issues long before they impact end users in a live environment. The quicker we get this feedback, the cheaper and easier it is to course correct. 1. Expanding the testing pyramid, from components to systems. The concept of the testing pyramid provides a useful mental model for structuring our tests and understanding their feedback scope. Unit tests base many fast-running tests focusing on isolated units of code, covered in Chapter 4. These provide the fastest, most granular feedback. Integration tests middle, fewer than unit tests, but more comprehensive, verifying interactions between different components or services. End-to-end tests top, the fewest but most complex tests, simulating real user journeys through the entire system. These provide feedback on the overall system's functionality from a user's perspective. As we move up the pyramid, tests become slower to run but cover a wider scope, providing different kinds of quality feedback. 2. Automated integration and end-to-end testing. While unit tests confirm the internal logic of a single function, software applications are rarely built from isolated parts. Components need to communicate, databases need to store data, and external services need to be called. Automated integration tests. These tests verify that individual modules or services interact correctly. For instance, testing if the user authentication service can successfully communicate with the user database, or if a payment gateway integration works as expected. The feedback here confirms that the pieces fit together and that contracts between services are observed. Automated end-to-end (E2E) tests. These are the big guns of functional testing, simulating entire user flows through the application, often interacting with the user interface. An E2E test for an e-commerce site might simulate a user logging in, searching for a product, adding it to the cart, and completing a purchase. While slower and more brittle than unit or integration tests, E2E tests provide invaluable feedback on the overall system's fitness for purpose and can catch critical issues that only manifest when all parts of the system are working together. Automating these ensures consistent and repeatable execution, providing continuous feedback on critical user paths. 3. Performance testing. Understanding behavior under load. A feature might function perfectly for one user, but what happens when thousands or millions of users try to access it simultaneously? Performance testing provides crucial feedback on the application's speed, stability, and scalability under varying workloads. Load testing simulates expected user traffic to see if the system performs adequately. Feedback includes response times, throughput, and resource utilization, CPU, memory, network. Stress testing pushes the system beyond its normal operating limits to determine its breaking point and how it behaves under extreme conditions. This feedback helps understand the system's resilience and capacity. Scalability testing evaluates the system's ability to handle increasing loads by adding resources, e.g., more servers. The feedback helps in capacity planning and architectural decisions. Performance feedback is vital for user satisfaction and operational stability. A slow application, even if functional, leads to user frustration and abandonment. 4. Security testing. Proactive vulnerability identification. In an age where data breaches are rampant, robust security is non-negotiable. Security testing aims to identify vulnerabilities and weaknesses that could be exploited by malicious actors. Vulnerability scanning. Automated tools scan code and deployed applications for known security flaws, misconfigurations, and outdated components. Penetration testing, pen testing. Ethical hackers simulate real-world attacks to find exploitable weaknesses. This provides hands-on feedback on the system's actual attack surface and resistance. Static application security testing, SAST, analyzes source code for security vulnerabilities before the code is run. Dynamic application security testing, DAST, tests the application in its running state, identifying vulnerabilities that appear during execution. The feedback from security testing is critical for protecting user data, maintaining trust, and complying with regulations. 5. User acceptance testing, UAT, the business's stamp of approval. This is where the direct user feedback loop from the planning phase comes full circle. While automated tests ensure the software functions technically, user acceptance testing, UAT, ensures it functions for the user and meets the business's actual needs. UAT involves actual end users or business stakeholders interacting with the almost finished product in a realistic environment. They perform tasks and scenarios that mirror their daily workflow, validating that the delivered solution aligns with their original requirements and expectations. The feedback received during UAT is qualitative and crucial. This doesn't work the way I expected. This process is too cumbersome. Or, this feature is missing a crucial piece. It's often the final opportunity to catch significant misalignments before general release, truly reinforcing the "are we building the right thing?" question. 6. Exploratory testing, human ingenuity and intuition. While automated tests are fast and repeatable, they can only verify what we expect to happen. They rarely find unexpected bugs or usability quirks that arise from novel interactions. This is where exploratory testing shines. Exploratory testing is a powerful, human-driven approach where skilled testers investigate the software without predefined test scripts. They simultaneously learn about the system, design tests, and execute them on the fly, driven by curiosity, intuition, and their experience with similar applications. It's about thinking outside the box, trying unusual inputs, and discovering unexpected behaviors. The feedback from exploratory testing often uncovers edge cases, complex sequence bugs, or subtle usability issues that no automated test or pre-written script could have anticipated. It complements automated testing by leveraging distinct human cognitive abilities. 7. A/B testing and experimentation, data-driven feature feedback. While often considered a post-deployment optimization, A/B testing is fundamentally a powerful feedback loop that spans both testing and production. Instead of guessing which version of a feature, UI element, or even a wording change will perform better, A/B testing allows you to test 2 or more variants simultaneously. A split of your user base, e.g., 50% see version A, 50% see version B is exposed to different experiences, and their behavior is measured against predefined metrics, e.g., conversion rate, click-through rate, time on page. The data collected provides objective feedback on which version drives better outcomes. This isn't about finding bugs, but about getting direct, empirical feedback on what resonates best with your users, driving continuous product improvement based on real-world interaction. The various forms of testing discussed in this chapter collectively form a comprehensive quality assurance safety net, providing continuous feedback on software correctness, performance, security, and usability. By embracing these diverse testing strategies and integrating them throughout the development pipeline, we significantly reduce the risk of releasing flawed software. This robust feedback prepares our application for its next critical journey, deployment and release, where an entirely new set of feedback mechanisms come into play to ensure a smooth transition to live operation. Chapter 6: Bridging the Gap. Feedback and Deployment and Release. After code has been carefully crafted and rigorously tested within development environments, it reaches a critical juncture: the transition into live production, where real users interact with it. Traditionally, this go-live moment was fraught with anxiety. It was often a high-stakes, manual process, performed infrequently, usually late at night or on weekends, with everyone holding their breath, hoping for the best. The feedback on whether the deployment succeeded was often immediate and painful. Either everything worked, or the phones started ringing off the hook with customer complaints. Modern software development, however, seeks to transform deployment from a terrifying cliff-edge jump into a series of small, safe, and controlled steps. This transformation is driven by sophisticated feedback loops that aim to detect problems before they impact all users, and to make the process of getting software to users as seamless and low-risk as possible. The seamless flow, continuous delivery, and continuous deployment. Building on the foundation of continuous integration, CI, discussed in Chapter 4, the concepts of continuous delivery, CD, and continuous deployment extend the automation and feedback philosophy right up to the point of release. Continuous delivery, CD. This practice ensures that software is always in a deployable state. Every change, after passing through automated tests and integrations, is automatically built into a release candidate. While the decision to deploy to production might still be manual, e.g., a product manager gives the final go-ahead, the process of getting it there is fully automated. The feedback here is constant. Is our software always ready to go live? Any break in the automated pipeline provides immediate feedback that the deployability itself is at risk. Continuous deployment. This takes continuous delivery a step further. If the release candidate passes all automated tests and quality gates, it is automatically deployed to production without human intervention. This requires an extremely high level of confidence in the automated testing and monitoring systems. The feedback loop here is incredibly tight. Software changes reach users within minutes or hours of being committed, providing real-world feedback almost instantly. The goal of both CD and continuous deployment is to make releases a routine, low-risk event, rather than an extraordinary one. This frequency and automation themselves create vital feedback. The smoother the pipeline, the more confidence the team has in their process. Deployment strategies for safety and informed feedback. Even with robust automated pipelines, directly deploying new code to all users carries risk. Sophisticated deployment strategies are designed to introduce changes gradually, monitor their impact, and provide early feedback, allowing for quick intervention if issues arise. Blue-green deployments. Imagine you have two identical, parallel production environments. Let's call them blue and green. At any given time, only one environment is live and serving user traffic, e.g., blue. When a new version of the software is ready, it's deployed to the inactive environment, e.g., green. This green environment can then undergo rigorous automated and manual testing in a production-like setting before any live user traffic is directed to it. Critically, these tests leverage the actual production infrastructure and data sources where possible, providing incredibly realistic feedback. Once confident, a simple switch of the network router instantly redirects all user traffic from blue to green. If any problems are detected post-switch, rolling back is as simple as switching traffic back to the original blue environment, which remains untouched and available. Feedback. This strategy provides invaluable feedback on the new version's stability and performance in a near-live state, before it becomes the primary user experience. The easy rollback mechanism is the ultimate feedback loop, telling you instantly if the new version is problematic. Canary releases. Named after the canaries used in coal mines to detect toxic gases, a canary release strategy involves rolling out a new version of software to a very small subset of real users, e.g., 1 to 5% of traffic, first. These users become the canaries in the coal mine. The operations team closely monitors the performance, error rates, and user feedback from this small group. If the canary group shows no significant increase in errors or performance degradation, the release is gradually rolled out to more users. If issues are detected, the traffic to the canary group can be immediately redirected back to the old version, minimizing the impact on the vast majority of users. Feedback. Canary releases provide crucial real-world feedback from a small, controlled sample of actual users, who might interact with the software in ways test environments couldn't fully simulate. This feedback is gathered in minutes or hours, allowing for proactive intervention before a broad impact. Feature flags, dark launching. Feature flags, also known as feature toggles or dark launching, decouple the deployment of code from the release of a feature. A feature flag is essentially a toggle built into the code that allows specific features to be turned on or off without redeploying the application. This means new, even experimental, features can be deployed into production, but kept dark, hidden for most users. They can then be enabled for internal teams, specific beta testers, or a small percentage of users, often combined with A/B testing, as revisited in Chapter 5. Feedback. Feature flags provide multiple layers of feedback. Operational stability. Is the new feature's code stable in a live environment, even if unseen by users? Controlled exposure. Allows for staged rollouts to specific user segments, getting focused feedback, e.g., this feature is only for our premium users initially. A/B testing facilitates direct, data-driven feedback on user behavior and preference between different versions of a feature. If a new feature performs poorly, it can be instantly turned off without a new deployment. The ultimate safety net, automated rollbacks. No matter how many precautions are taken, sometimes things still go wrong. When an issue is detected post-deployment, the ability to automatically roll back to a known good state is paramount. This isn't just about restoring service. It's a critical feedback mechanism. A successful automated rollback loop tells the organization that their deployment process is resilient and that they have a rapid response plan for when things inevitably go awry. It provides immediate reassurance and allows teams to debug the failed deployment in a calm environment, knowing that users are back on a working version. Pre-deployment health checks and post-deployment validation. Beyond the sophisticated strategies, direct automated checks provide immediate feedback on the deployment process itself. Pre-deployment health checks. Before any code is deployed, automated scripts verify that the environment is ready. Is there enough disk space? Are all necessary services running? Is the database connection valid? This pre-flight check provides critical feedback. Are we even capable of deploying successfully right now? Post-deployment validation, smoke tests. Immediately after a new version is deployed, automated smoke tests run quick, high-level checks against the newly deployed application. Can it load the home page? Can a user log in? Can a core transaction complete? This provides the fastest feedback on whether the deployment was successful and the application is fundamentally operational, giving the all-clear signal or an immediate red flag. The power of small, frequent deployments. Underlying all these strategies is a core principle: small, frequent deployments. Instead of massive releases with hundreds of changes that occur once every few months, modern teams aim for many small deployments every day or week. This approach offers enormous feedback advantages: reduced risk. A small change has a small blast radius if something goes wrong. It's easier to find the root cause of an issue when only a few things have changed. Faster debugging. Fewer changes mean fewer places to look when a bug appears. Quicker feedback. Users and monitoring systems see new features and report issues much faster, allowing the team to iterate and improve more rapidly. Less buildup of pressure. Deployments become routine, not heroic events, reducing stress and human error. In essence, shifting to small, frequent, and controlled deployments, supported by robust automated checks and intelligent rollout strategies, transforms the release process itself into a continuous feedback loop. It's no longer a one-way street of pushing code out, but a dynamic, self-correcting system that constantly validates and improves its ability to deliver value to users. With the software now live and serving users, the ultimate feedback loop begins, monitoring, observing, and learning from the system's real-world behavior in production. Chapter 7. The Living System. Feedback from Production and Operations. The previous chapters have guided us through the meticulous processes of planning, designing, building, testing, and deploying software. While these earlier stages are vital for bringing a product to life, they are, in many ways, rehearsals. The true performance begins when the software is running in production, interacting with real users, processing real data, and facing the unpredictable realities of the internet and hardware. This is where the ultimate, most comprehensive feedback loop takes center stage. Learning from the living system. Once software is live, it becomes a dynamic entity. It's no longer just code, it's a service. How users interact with it, how it performs under load, how it responds to unexpected events. All of this generates a torrent of invaluable feedback. This feedback from production and operations is crucial because it often uncovers issues, user behaviors, and performance characteristics that are impossible to fully replicate in even the most sophisticated test environments. The ultimate feedback loop, real-world usage data. In production, every click, every transaction, every error, every API call, and every millisecond of latency tells a story. This real-world usage data is the richest form of feedback, providing undeniable evidence of whether the software is truly delivering value and operating reliably. The challenge and the opportunity lies in effectively collecting, analyzing, and acting upon this vast sea of information. 1. Monitoring and observability. Seeing inside the black box. To understand our living system, we need to make it observable. This means instrumenting our applications and infrastructure to continuously emit data that provides insight into their internal states and behaviors. Logs. These are immutable, time-stamped records of events that occur within an application or system. Logs tell us what happened, e.g., a user logged in, an order was placed, an error occurred. Centralized logging systems aggregate logs from across many services, making it possible to trace user journeys or diagnose complex distributed system issues. Reviewing logs provides a narrative of events, offering crucial diagnostic feedback. Metrics. These are numerical measurements collected over time, representing the health or performance of a system, e.g., CPU utilization, memory consumption, network latency, request rates, error counts, database query times. Dashboards powered by these metrics provide a high-level overview, indicating how well the system is performing and allowing for trend analysis. Sudden spikes or drops in key metrics are immediate feedback that something is amiss. Traces. In modern distributed systems, microservices, a single user request might traverse dozens of different services. Tracing helps us follow the path of a single request across these services, providing a detailed view of why something is slow or failing. It offers invaluable feedback for pinpointing performance bottlenecks or errors within complex service interactions. The combination of logs, metrics, and traces forms the pillars of observability, allowing engineers to ask arbitrary questions about their systems and get answers, even for issues they didn't anticipate. This comprehensive view provides continuous, objective feedback on the operational health and performance of the software. 2. Alerting and incident management. The system cries for help. Monitoring and observability are passive. They tell us what's happening. Alerting is active. It tells us when something unexpected or critical is happening, demanding immediate attention. Alerts are configured based on thresholds in our metrics or specific patterns in our logs, e.g., CPU usage above 80% for 5 minutes, more than 105 XX errors per minute. Timely alerts. The feedback from alerts is urgent. It prompts teams to investigate and resolve issues before they significantly impact users or degrade service quality. Incident management. When an alert escalates into a full-blown incident, a service outage or major degradation, a structured incident management process kicks in. This involves rapid response, diagnosis, mitigation, and eventual resolution. Crucially, post-incident reviews, often called blameless postmortems, are a vital feedback mechanism. They analyze what went wrong, why it went wrong, and what steps can be taken to prevent recurrence. This feedback feeds directly back into the development process, improving system resilience and operational practices. 3. Direct user feedback channels, the voice of the customer. Beyond automated metrics, the most direct form of feedback comes from the people actually using the software. In-app feedback mechanisms. Simple send feedback buttons or forms embedded directly within the application make it easy for users to report bugs, suggest features, or express frustration without leaving their workflow. Support tickets and help desks. Customer support teams are an invaluable source of structured user feedback. Trends in support calls or recurring issues highlighted in tickets provide direct insight into common pain points, confusing UIs, or critical bugs. Surveys and user interviews. Soliciting feedback through targeted surveys, e.g., Net Promoter Score, CSAT, or direct interviews can uncover deeper qualitative insights into user satisfaction, unmet needs, and the overall user experience. Social media and community forums. Often unsolicited, discussions on platforms like Twitter, Reddit, or dedicated community forums can provide early signals about user sentiment, emerging issues, or desired features. This qualitative feedback from users is often less about technical performance and more about product performance. Is the software intuitive? Is it solving their actual problems? Is it delightful to use? This feedback loops directly back to product managers and designers, guiding feature prioritization and future development. For deeper dive, A/B testing and experimentation in production. While introduced in Chapter 5, A/B testing truly comes into its own in the production environment. It moves beyond just theoretical validation to real-world behavioral science. By exposing different groups of live users to variations of a feature, a UI element, or even marketing copy, and measuring their responses, e.g., conversion rates, engagement, time spent, A/B testing provides empirical, data-driven feedback on what truly works and what doesn't. This feedback is critical for optimizing product features, user flows, and ultimately, business outcomes. It shifts decision-making from opinion-based to evidence-based, allowing continuous iteration and improvement based on actual user behavior. 5. Chaos engineering, proactively finding weaknesses. Sometimes, the best way to get feedback on a system's resilience is to actively break it. Chaos engineering is the practice of intentionally injecting failures into a distributed system to identify weaknesses and build confidence in its ability to withstand turbulent conditions. Think of it as an immune system for your software. By periodically and deliberately introducing controlled infections, e.g., taking down a server, introducing network latency, saturating a database, teams can observe how the system responds. Do alerts fire correctly? Does the system self-heal? Does it degrade gracefully? The feedback gained from chaos experiments helps teams proactively identify single points of failure, improve recovery mechanisms, and harden their systems before real-world outages occur. 6. Site reliability engineering, SRE. Operationalize feedback. The principles of site reliability engineering, SRE, pioneered at Google, fundamentally integrate operational feedback into the software development process. SREs treat operations as a software problem, focusing on automating manual tasks, defining clear service level objectives, SLOs, and service level indicators, SLIs, and dedicating engineering time to improving the reliability and performance of systems. SRE practices emphasize using data, metrics, logs, traces to inform decisions, automating mundane operational tasks to free up engineers for reliability improvements, defining error budgets. If a service starts exceeding its allowed error rate, the team must prioritize stability over new features. providing a clear feedback mechanism that operational health needs immediate attention. SRE transforms operational feedback from a reactive firefighting exercise into a proactive engineering discipline that continuously feeds insights back into the product development lifecycle, using production data to drive the next cycle of development. All the feedback gathered from production, the performance data, the user interaction patterns, the incident reports, the direct user comments, must not reside in isolation. It forms the most potent input for the next cycle of development. Performance bottlenecks identified through metrics lead to engineering refactoring efforts. Recurring support tickets highlight areas for UX improvements or bug fixes. A/B test results dictate which version of a feature gets released globally. Blameless postmortems drive architectural changes or improvements in deployment processes. This continuous flow of information from the wild back to the drawing board ensures that development efforts are always aligned with real-world needs and challenges. The software system, once deployed, becomes its own best teacher, constantly informing and refining its future evolution. With this in-depth understanding of how production feedback fuels improvement, we can now pivot from the technical mechanisms to the human element. For all these sophisticated tools and processes to work, a supportive culture is paramount. Without it, feedback can become a source of blame rather than growth, a topic we will delve into in the next chapter. Chapter 8, Beyond Tools, the Cultural Foundation of Feedback. We've journeyed through the various stages of the software development lifecycle, exploring the myriad of ways continuous feedback loops are woven into the fabric of planning, building, testing, and operating digital products. From early design critiques to real-time production monitoring, it's clear that without these technological and process-based mechanisms, modern software delivery would grind to a halt. However, relying solely on tools and processes, no matter how sophisticated, is akin to providing a highly advanced surgical robot to a team of surgeons who don't trust each other, refuse to share information, or fear making a mistake. The robot might be flawless, but the patient's outcome would still be uncertain. In the context of continuous feedback loops, technology alone isn't enough. The human element is paramount. The most advanced monitoring dashboards, the most efficient CI/CD pipelines, and the most comprehensive testing suites are valuable only if the people using them are willing to receive, internalize, and act upon the feedback generated. This requires a specific kind of organizational culture, one rooted in trust, transparency, continuous learning, and a shared commitment to improvement. The power of psychological safety and trust. Imagine a team where raising a concern about a design flaw is met with defensiveness, or reporting a bug is seen as admitting failure. In such environments, individuals will naturally shy away from providing critical feedback, even when it's vital for project success. Conversely, in an environment of psychological safety, team members feel safe to take interpersonal risks, to speak up, ask questions, admit mistakes, challenge the status quo, and offer candid feedback, even if it feels uncomfortable. Amy Edmondson, a Harvard professor who coined the term, defines psychological safety as a shared belief that the team is safe for interpersonal risk-taking. When psychological safety is present, feedback is given and received openly. Developers are keen to get constructive criticism on their code, designers welcome user insights into their prototypes, and product managers actively solicit feedback on their feature ideas. Mistakes become learning opportunities. Instead of hiding errors, they are brought to light quickly, allowing the team to learn from them collectively. Continuous improvement thrives. Because people aren't afraid of admitting what they don't know or what went wrong, they are more eager to find solutions and improve processes. Building psychological safety requires intentional effort from leadership and every team member. It means fostering an atmosphere where honesty is valued, curiosity is encouraged, and blame is replaced with empathy and problem-solving. The learning organization, embracing mistakes through blameless postmortems. In high-stakes industries like aviation, medicine, and now increasingly in software, a fundamental shift has occurred in how errors are handled. When an incident occurs in aviation, the goal of the investigation is not to find a scapegoat, but to understand all contributing factors: technical, procedural, human, and environmental, to prevent future occurrences. This same principle applies to software development through blameless postmortems, also known as blameless incident reviews or retrospectives. When a system outage occurs, a critical bug slips into production, or a project misses a deadline, the immediate human tendency might be to find who is responsible. However, a blameless postmortem instead focuses on answering, what happened? Why did it happen? Going beyond individual actions to systemic factors. What did we learn? What actions can we take to prevent recurrence or mitigate impact in the future? By removing the fear of punishment, teams can openly discuss the true causes of problems, whether they are code defects, process gaps, communication breakdowns, or infrastructure failures. This radical transparency turns costly incidents into invaluable learning experiences, feeding directly back into process improvements, architectural changes, and enhanced team knowledge. It cultivates a learning organization that views every stumble as an opportunity to get stronger. Empowering teams to act on feedback. Having sophisticated feedback mechanisms and a culture of psychological safety won't yield results if teams aren't empowered to act on the feedback they receive. This means autonomy, giving teams the authority and resources to make decisions and implement changes based on the feedback they gather. If a team identifies a persistent error pattern in production logs, they should be able to prioritize fixing it without excessive bureaucratic hurdles. Clear ownership, ensuring that each piece of feedback has a clear owner responsible for addressing it. Whether it's a bug report, a user suggestion, or a performance bottleneck, someone needs to shepherd it toward a resolution. Dedicated time for improvement, protecting time for teams to address technical debt, refactor problematic code, or improve their development processes. Ignoring this necessary rework based on feedback only accrues more problems down the line. When teams are empowered, the feedback loops become closed loops, sensing a problem, analyzing it, acting on it, and then verifying the improvement. This creates a virtuous cycle of continuous improvement and strengthens team commitment. The leader's role, fostering and championing a feedback-rich environment. Leaders play a pivotal role in shaping the culture around feedback. They are the primary architects of psychological safety and the chief champions of continuous improvement. Their actions, more than their words, define the environment. Lead by example. Leaders must openly acknowledge their own mistakes, ask for feedback on their performance, and demonstrate a genuine willingness to learn. If a leader appears defensive, their team will quickly follow suit. Create safe spaces. Actively facilitate blameless postmortems and retrospectives. Ensure these discussions remain constructive and future-oriented. Protect teams from external blame when incidents occur. Invest in feedback mechanisms. Allocate resources for tools, training, and processes that enable effective feedback loops, e.g., dedicated time for code reviews, resources for monitoring infrastructure. Promote transparency. Share information openly, good and bad. This builds trust and ensures everyone understands the context and impact of their work. Recognize and reward learning. Celebrate discoveries and improvements, not just flawless execution. This reinforces the value of experimentation and learning from failures. A leader who views feedback not as critique, but as a gift, who champions continuous learning, and who prioritizes team well-being, lays the strongest foundation for effective continuous feedback loops. Cross-functional collaboration as a continuous feedback loop. Finally, the cultural shift also involves breaking down traditional organizational silos. When different functions, e.g., product, design, development, operations, support, work in isolation, feedback becomes fragmented and delayed. True continuous feedback thrives on cross-functional collaboration. This means integrated teams, having designers, developers, testers, and product owners working together daily, co-located, or virtually. Shared goals, aligning everyone around common product and business objectives rather than departmental metrics. Continuous communication, establishing regular, informal channels for dialogue and information exchange beyond formal meetings. Mutual empathy, each function understanding the challenges and perspectives of the others. A developer understanding the support team's pain points with a feature, or a product manager appreciating the operational challenges of a new service. When these functions seamlessly exchange information and perspectives, they create their own implicit feedback loops. A developer can get instant design clarification. A product owner can quickly validate a new idea with an engineer, and the support team's insights can directly inform the next sprint's priorities. This constant inter-team dialogue is a powerful, organic form of continuous feedback. In summary, while tools and processes provide the structure for continuous feedback, it is the underlying culture that breathes life into them. A culture built on psychological safety, blameless learning, empowerment, strong leadership, and seamless collaboration transforms feedback from a chore into the engine of organizational growth and innovation. Without this fertile ground, even the most meticulously designed feedback loops risk becoming mere rituals, divorced from their true purpose of driving constant improvement. However, even in the most well-intentioned cultures, challenges inevitably arise. The volume of feedback can be overwhelming, and conflicting signals can lead to paralysis. Our next chapter will dive into common pitfalls and practical strategies for navigating them effectively. Chapter 9: Common Pitfalls and How to Overcome Them. By now, it should be abundantly clear that continuous feedback loops are indispensable for building high-quality, relevant software in today's dynamic environment. We've explored the methods, the technologies, and the cultural underpinnings necessary for their success. However, the path to truly effective feedback isn't without its obstacles. Even the most well-intentioned teams and organizations can stumble. This chapter addresses common pitfalls that hinder the benefits of continuous feedback and offers practical strategies to navigate them. 1. Information overload and feedback fatigue. The pitfall: as we've seen, feedback comes from everywhere. User stories, design critiques, unit tests, static analysis, code reviews, CI/CD pipelines, production monitoring, user support tickets, A/B tests, and more. This torrent of information can quickly become overwhelming. Teams can drown in data, alerts can become noisy, and individuals might feel constantly nitpicked or simply too tired to process yet another piece of feedback. This leads to feedback fatigue, where vital signals are ignored or dismissed. How to overcome it: prioritize and filter. Not all feedback is equally important or urgent. Establish clear criteria for what constitutes critical, high-priority feedback, e.g., security vulnerabilities, critical production bugs, major user blockers, versus minor suggestions or long-term improvements. Use dashboards and alerting systems to highlight only the most pertinent information. Actionable feedback. Ensure feedback is specific, objective, and actionable. Instead of "this UI looks bad," provide "the contrast on this button is too low," making it difficult for visually impaired users to see it. Automated tools should provide clear, understandable messages. Automate where possible. Many low-level, repetitive feedback items, like code formatting, should be handled by automated tools, linters, static analyzers that provide immediate, non-intrusive suggestions, freeing up human reviewers for more complex, conceptual feedback. Control the input stream. Don't collect data just because you can. Be intentional about what metrics you track and what channels for user feedback you open. Only gather information you are prepared to act upon. 2. Analysis paralysis, getting stuck in data without action. The pitfall, closely related to information overload. Analysis paralysis occurs when teams spend too much time analyzing feedback and data, debating solutions, and perfecting plans without actually taking action. The fear of making the wrong decision or the sheer volume of choices can lead to inertia. How to overcome it: bias for action, small batches, embrace the agile principle of done is better than perfect. Aim for small, incremental changes based on feedback. Instead of a perfect solution, seek a good enough solution that can be deployed quickly and provide new feedback. Define clear ownership. Assign explicit responsibility for acting on specific types of feedback. Who is responsible for reviewing and prioritizing support tickets? Who owns closing out architecture review action items? Timebox discussions. Set specific limits for how long a team will analyze a problem or debate a solution. If a consensus isn't reached, use decision-making frameworks, e.g., rough consensus, prototyping multiple options to move forward. Hypothesis-driven development. Frame changes based on feedback as hypotheses. We believe this change will result in this outcome for these users. This encourages execution to validate the hypothesis rather than endless debate. 3. Resistance to change and not invented here syndrome. The pitfall: even with clear feedback indicating a need for change, teams or individuals can resist. This can stem from a comfort with existing processes, a fear of the unknown, or the not invented here syndrome, where ideas or criticisms from external sources, even users, are dismissed. Defensive reactions to feedback can stifle improvement. How to overcome it? Cultivate psychological safety, revisited. As discussed in Chapter 8, a culture of trust and non-blame is fundamental. When people feel safe, they are more open to admitting errors and trying new approaches. Focus on the why. When presenting feedback, explain the underlying problem it addresses and the benefit of the proposed change. Don't just present the what. Focus on how the change benefits the user, the team, or the business. Involve them in the solution. People are more likely to support changes they helped shape. Involve those most affected by the feedback in brainstorming and designing solutions. Show success stories. Highlight examples where acting on feedback led to significant improvements. Demonstrate the positive impact of embracing change. Provide training and support. If the feedback suggests a need for new skills or tools, provide the necessary resources and training to ease the transition. 4. Siloed teams and communication breakdowns. The pitfall: in large organizations, or even smaller ones with traditional departmental divides, feedback can get trapped within specific teams, e.g., development doesn't see user support tickets, QA is disconnected from product design, operations is separate from development. This creates a lag in the feedback loop and a lack of shared understanding. How to overcome it? Cross-functional teams. Organize teams around products or services rather than functional silos. This fosters direct, continuous communication and shared responsibility, as seen in Agile and DevOps. Shared visibility. Implement shared dashboards, communication channels, and tooling that provide everyone product, design, dev, ops support with access to relevant feedback data. Regular syncs and retrospectives. Hold regular cross-functional meetings, like product reviews, incident postmortems, or even informal coffee breaks that encourage dialogue between different disciplines. Empathy building. Encourage job shadowing or rotations between roles, e.g., a developer spending a day with the support team to build empathy and understanding of different perspectives. 5. Technical debt hindering the implementation of feedback loops. The pitfall: sometimes teams inherently understand the value of a feedback loop, e.g., we need automated end-to-end tests. We need better monitoring. But their existing codebase is such a tangled mess of technical debt that implementing these improvements seems insurmountable. Legacy systems, lack of modularity, and tight coupling can make it incredibly difficult to instrument, test, or rapidly iterate. How to overcome it? Prioritize technical debt as a product feature. Make tackling technical debt an explicit backlog item alongside new features. Frame it in terms of business value, e.g., reducing technical debt in the payment module will decrease bugs by 15% and increase deployment frequency. Boy Scout rule: encourage developers to leave the campground cleaner than you found it. Whenever working on a piece of code, take a few minutes to improve it slightly, whether it's refactoring a function, adding a unit test, or removing dead code. These small, continuous improvements chip away at the debt. Incremental improvements. Don't try to solve all technical debt at once. Break down large refactoring efforts into small, manageable chunks that can be integrated gradually. Dedicated enabling teams. For very large organizations, consider having small, dedicated teams focused on building and maintaining the infrastructure, e.g., CI/CD pipelines, monitoring platforms, that empower other product teams to implement their feedback loops. 6. Measuring the impact of feedback, not just its existence. The pitfall: it's easy to track the volume of feedback, e.g., we do 5 code reviews a day. We have 100 alerts. It's much harder to measure its quality and impact. Are code reviews actually reducing bugs? Is the feedback leading to better user satisfaction? Without measuring the impact, feedback loops can become performative rather than truly effective. How to overcome it? Define clear metrics, KPIs. As we'll discuss more deeply in the next chapter, connect feedback to measurable outcomes. For instance, code review feedback defect escape rate. Are fewer bugs making it to production post-review? User feedback CSAT NPS, feature adoption. Is user satisfaction improving, or is the new feature being used more? Monitoring alerts, MTTR, mean time to recovery. Are we identifying and recovering from incidents faster? Correlate changes with outcomes. Actively track improvements that were a direct result of specific feedback. This helps validate the feedback loop and demonstrate its value. Regular review of metrics. Periodically review the key performance indicators related to feedback loops to ensure they are actually driving desired results. Adjust the feedback mechanisms or the process based on these metrics. Strategies for prioritizing and acting on feedback effectively. The overarching solution to many of these pitfalls is a disciplined approach to feedback prioritization and action. Create a backlog. Treat feedback as input to a prioritized backlog. Whether it's a product backlog, a bug backlog, or a technical debt backlog, ensure all valuable feedback has a place and is considered for future work. Product thinking. Frame all feedback through the lens of product value. Will addressing this feedback enhance user experience, improve system reliability, or contribute to business goals? Closed-loop verification. Always ensure that feedback leads to action and that the impact of that action is then verified. This completes the loop and builds confidence in the feedback system. We got this feedback, we made this change, and here's the data that shows it worked or didn't. Example: a customer submits a support ticket about a confusing error message. Feedback received. The team identifies the source of the message. Analysis: they improve the message and add better logging. Action: they deploy the change and monitor logs and support tickets for a reduction in similar errors. Verification. Navigating these common pitfalls requires a blend of technical expertise, organizational discipline, and a strong cultural commitment to continuous improvement. It's an ongoing journey, but by being aware of these challenges and implementing proactive strategies, organizations can maximize the transformative power of continuous feedback loops. The ultimate test of these efforts is their impact on the bottom line, which brings us to our next chapter: Measuring Success. Chapter 10, Measuring Success and Continuous Improvement. We have traversed the entire landscape of continuous feedback loops, from their strategic origins in planning and design to their intricate operation in coding, testing, deployment, and live production. We've seen how integrating feedback at every stage fosters quality, speed, and relevance, and how a supportive culture is essential for feedback to thrive. But how do we know if all these efforts are actually paying off? How do we measure the efficacy of our feedback loops and, by extension, the health and maturity of our software development process? The answer lies in measurement. Just as feedback helps us course-correct our software, measuring the impact of our feedback loops provides the ultimate feedback on our development process itself. It allows us to validate our investments, identify new bottlenecks, justify improvements, and continuously optimize how we build and deliver software. Without reliable metrics, continuous improvement becomes a matter of guesswork and intuition rather than a data-driven discipline. Defining success, key metrics for effective feedback loops. The success of continuous feedback loops isn't solely defined by the number of feedback channels you have, but by how effectively that feedback drives positive outcomes. These outcomes can be quantitative, qualitative, and span different aspects of the software delivery process. Let's explore some key metrics that serve as a compass for success. 1. Delivery performance metrics, the 4 key metrics of DevOps. Research, particularly from the DORA, DevOps Research and Assessment, team, has consistently shown that 4 core metrics predict an organization's ability to deliver software quickly, reliably, and with high quality. These metrics are direct indicators of how well continuous feedback loops are functioning throughout the pipeline. Lead time for changes. This measures the time it takes for a committed code change to be successfully running in production. It's about the speed of the entire development and delivery loop. A short lead time indicates highly effective CI/CD pipelines, automated testing, and a streamlined deployment process, all underpinned by rapid feedback. Deployment frequency. This refers to how often an organization successfully delivers changes to production. High deployment frequency is a hallmark of strong continuous feedback. It implies small, low-risk changes, robust automation, and the confidence to release often because issues are quickly detected and resolved. Mean time to restore (MTTR). When an incident occurs in production, e.g., an outage or service degradation, MTTR measures the average time it takes to restore service. A low MTTR signifies excellent operational feedback loops, effective monitoring and alerting, well-practiced incident response, and the ability to quickly diagnose and remediate problems. Change failure rate. This is the percentage of changes to production that result in a degraded service, requiring remediation, e.g., a rollback, hotfix, or patch. A low change failure rate indicates the effectiveness of all preceding feedback loops, from planning and design, building the right thing, to comprehensive testing, building the thing right, and safe deployment strategies. These 4 metrics provide a holistic view of the development pipeline's agility, reliability, and flow, all of which are direct consequences of robust continuous feedback. 2 quality and product value metrics. Beyond the delivery pipeline itself, we need to measure the quality of the software and its impact on users and the business. Defect escape rate. This metric tracks the number or proportion of defects that escape detection in development testing phases and are found by users in production. A high escape rate suggests weaknesses in testing feedback loops, unit, integration, E2E, UAT, while a low rate indicates effective quality assurance and shifting left practices. Service level objectives, SLOs, and service level indicators, SLIs. Introduced in Chapter 7, SLIs are specific, measurable metrics, e.g., 99.9% uptime, login response time under 2 seconds. SLOs are the targets set for these SLIs. Continuously monitoring, these provides immediate feedback on system health and reliability from an operational perspective, directly impacting user experience. Customer satisfaction, CSAT, and Net Promoter Score, NPS. These metrics provide direct feedback on user sentiment. CSAT usually asks, "How satisfied are you with X?" while NPS asks, "How likely are you to recommend us to a friend?" Tracking these over time provides critical qualitative and quantitative feedback on whether the software is meeting user expectations and delivering perceived value. Feature usage/adoption rates. Are newly released features being used? Are users adopting new workflows? If a feature designed to solve a problem sees little or no adoption, it's a critical piece of feedback that either the problem wasn't real, the solution wasn't good, or its discoverability was poor. This data directly informs product development priorities. Conversion rates/business key performance indicators, KPIs. Ultimately, software exists to serve a business purpose, e.g., increase sales, reduce costs, improve efficiency. Linking software changes to core business KPIs, e.g., e-commerce conversion rates, customer retention, service costs, provides the ultimate feedback on its contribution to strategic goals. Intrinsic feedback loops for teams, retrospectives. While the metrics above provide quantitative feedback, a crucial qualitative feedback loop exists within the rhythm of Agile and DevOps teams. Retrospectives. Typically held at the end of each sprint or major project milestone, retrospectives are dedicated, time-boxed meetings where the team reflects on its recent work. The simple questions asked during a retrospective form a powerful feedback mechanism. What went well? What could be improved? What will we commit to trying differently next time? Retrospectives foster continuous self-assessment and adaptation at the team level. They allow teams to inspect and adapt their process, not just their product. This internal feedback loop helps teams to identify and address bottlenecks, improve collaboration, refine their tooling, and strengthen their working relationships. They are the bedrock of a learning organization. Optimizing the entire value stream mapping. To truly understand and improve the flow of value from an idea to a user, organizations can employ value stream mapping. This technique involves visually charting all the steps involved in delivering a product or service, from the initial request to its delivery to the customer. For each step, teams measure attributes like process time, time spent actively working; wait time, time spent waiting for the next step; handoffs and cues, decision points. Value stream mapping helps teams gain a holistic understanding of their end-to-end delivery process, often revealing significant periods of waste, non-value-adding activities, or waiting. The insights gained provide invaluable feedback on where the biggest opportunities for improvement lie, e.g., we spend 2 weeks waiting for security review, or our deployments take 3 days and are mostly manual. By identifying these points, teams can focus their continuous improvement efforts on reducing lead time across the entire value stream. Benchmarking and continuous self-assessment. Effective measurement isn't a one-off activity, it's a continuous practice. Benchmarking. Periodically, organizations can compare their performance metrics against industry benchmarks or best practices. Reports like the DORA State of DevOps report offer valuable insights into what high-performing teams achieve. This external comparison provides feedback on where an organization stands relative to its peers and identifies areas where significant gains are possible. Internal trend analysis. More importantly than external comparison is tracking trends internally. Is lead time for changes decreasing? Is defect escape rate improving? Are CSAT scores rising? This continuous self-assessment provides feedback on your own journey of improvement, celebrating progress and highlighting areas that require more attention. The long-term business impact of a robust feedback culture. The ultimate measure of success for continuous feedback loops is their long-term impact on the business. When effectively implemented, CFLs don't just optimize technical processes, they become a competitive differentiator. Faster time to market. By continuously learning and adapting, organizations can bring new features and products to market much more quickly, capitalizing on opportunities and responding to threats. Higher quality products. Fewer bugs, better performance, and greater user satisfaction lead to stronger brand reputation and customer loyalty. Increased innovation. Teams confident in their ability to detect and correct issues quickly are more likely to experiment and innovate, knowing that failure is a learning opportunity, not a catastrophe. Reduced costs. Addressing problems early, optimizing processes, and building the right product reduces rework, optimizes resource allocation, and fosters efficiency. Improved employee morale. Teams that receive clear, actionable feedback, see the impact of their work, and continuously get better are more engaged, productive, and less prone to burnout. Connecting software development activities directly to these business outcomes closes the final feedback loop. It demonstrates that the investment in continuous feedback loops is not merely a technical endeavor, but a strategic imperative that directly contributes to an organization's agility, resilience, and success in the digital age. We have explored the why and how of continuous feedback. With a solid understanding of measurement and improvement, we are now poised to look to the future. Our final chapter will explore the evolving landscape of software development and how feedback loops will continue to shape what comes next. Chapter 11, The Feedback Horizon. What comes next? We have traversed the complete journey of continuous feedback loops, from their foundational principles and historical imperative to their practical application across the entire software development lifecycle. We've dissected how feedback fuels planning, design, coding, testing, deployment, and crucial operations. And we've emphasized the indispensable role of culture and measurement in making these loops truly effective. Software development, once a sequential, rigid process, has transformed into a dynamic, adaptive ecosystem, constantly learning and self-correcting. But the story of continuous feedback is far from over. The landscape of software development is in perpetual motion, driven by new technologies, increasing complexity, and ever-escalating user expectations. Looking ahead, the role of feedback loops will only become more sophisticated, more automated, and even more central to the creation and maintenance of digital products. The evolving landscape and its impact on feedback. Several key trends are shaping the future of software development, and each magnifies the importance of advanced feedback mechanisms. Further distribution and decentralization. As microservices and serverless architectures become standard, systems become less monolithic and more distributed. This increases complexity in terms of monitoring, tracing, and understanding overall system behavior. Feedback loops for operations and security will need to become even more granular and sophisticated to manage this distributed landscape. Edge computing and IoT. Software is no longer confined to data centers or mobile devices. It's moving to the edge, cars, factories, smart city infrastructure, and countless IoT devices. Collecting, processing, and acting on feedback from these diverse and often remote environments presents unique challenges and opportunities for ultra-low latency feedback loops. Hyper-personalization. Users expect experiences tailored precisely to their needs and preferences. Achieving this requires continuous, real-time feedback on individual user behavior, preferences, and context, driving adaptive interfaces and dynamic content. Cybersecurity threats. The sophistication of cyber threats continues to evolve. Feedback loops, especially in security testing and production monitoring, must become predictive and adaptive, capable of identifying and mitigating novel attack vectors rapidly. Sustainability and green computing. As the environmental impact of computing becomes more salient, feedback loops will extend to resource consumption and energy efficiency. Monitoring and optimizing carbon footprints of software will become a new dimension of performance feedback. The role of artificial intelligence and machine learning in automating feedback. Perhaps the most transformative development impacting feedback loops is the accelerating maturation of artificial intelligence, AI, and machine learning, ML. These technologies are no longer just about building intelligent features into software. They are increasingly being used to make the process of building and operating software smarter. Automated anomaly detection. Instead of relying on static thresholds, ML algorithms can learn the normal behavior of a system from vast amounts of operational data, logs, metrics, traces. They can then automatically flag subtle anomalies that human operators or simple rules might miss, providing proactive feedback on impending issues before they escalate. Predictive analytics in operations. ML can analyze historical performance data to predict future system states. For example, predicting when a server will run out of capacity or when a network component is likely to fail, allowing for proactive maintenance and resource provisioning. This shifts operational feedback from reactive, after a failure, to predictive, before a failure. Intelligent alerting and noise reduction. AI can help filter through the deluge of monitoring data, correlating related events and suppressing irrelevant alerts. This reduces feedback fatigue, ensuring that human operators are only alerted to truly actionable issues. Log analysis and root cause analysis. ML models can rapidly pore over petabytes of log data, identifying patterns and correlations that point to the root cause of an incident far faster than a human could, providing accelerated diagnostic feedback. Automated code review and bot assistance. Advanced AI models are now capable of recommending code improvements, identifying potential bugs, or even suggesting refactors during the coding phase, providing instant, intelligent peer feedback. AI-powered bots can automatically generate or update test cases based on code changes, closing testing loops with minimal human intervention. The vision of self-optimizing and self-healing software systems, the ultimate aspiration of highly automated and intelligent feedback loops, is the creation of self-optimizing and self-healing software systems. Imagine a financial application that, upon detecting a slight increase in latency for a particular service, doesn't just alert an engineer. It automatically spins up additional server instances, reroutes traffic to healthier components, and potentially even executes a small, localized code update to address the issue, all without human intervention. This vision involves autonomous feedback action loops. Systems continuously monitor their own performance and behavior, make decisions based on predefined policies and learned models, and enact changes to themselves in real time. Adaptive architectures. Software that can dynamically reconfigure itself, scale components up or down, or even switch between different algorithms based on current load, user behavior, or external conditions. Proactive resilience. Systems that don't just react to failures, but anticipate them, taking preventative measures or isolating problematic components before they impact user experience. While still largely a theoretical ideal for complex systems, components of self-optimization and self-healing are already integrated into large-scale cloud platforms and highly mature operational environments, embracing the journey of never-ending improvement. As we stand at the threshold of this exciting future, it's critical to remember that underlying all these technological advances is the enduring principle of continuous improvement. The tools and techniques will change, but the fundamental human drive to create better, more reliable, and more valuable software will remain. For those involved in software development, this means cultivating an always learning mindset. The pace of change demands continuous education and adaptation. The best professionals will be those who actively seek out new forms of feedback and new ways to leverage it. Maintaining the human touch. While AI will automate many aspects of feedback processing and action, human insight, empathy for the user, and critical thinking for complex problem-solving will remain indispensable. The human element of culture, psychological safety, and blameless learning will be even more crucial to ensure these powerful automated systems are used wisely and ethically. Focusing on value. With an abundance of data and automation, the challenge will shift to discerning what truly matters. Effective feedback loops, whether manual or AI-driven, must always connect back to delivering tangible value to users and the business. The journey of continuous feedback is, by its very nature, a journey without an end. Software is never truly finished. It is perpetually evolving, improving, and adapting. By wholeheartedly embracing the philosophy of continuous feedback, by building robust systems for sensing, analyzing, acting, and observing, and by fostering a culture of relentless learning, we equip ourselves not just to survive, but to thrive in the complex, exhilarating, and ever-changing world of software development. May your loops always be continuous, and your improvements never-ending.